For this example, we're going to sketch the region R and set up and evaluate the integral. This is a double integral. R is the region of x e to the y squared times your differential area, dA. So it's important for us to be able to sketch the region and determine whether to draw vertical or horizontal rectangles. And we're going to replace that differential area dA with dy dx or dx dy. Let's sketch the region bounded by y is equal to 1, x is equal to 0, y is equal to x squared in Q1 or quadrant 1. Okay, so if we sketch at quadrant 1, we have our x-axis and our y-axis. The equation y is equal to 1 is a horizontal line through 1. The line x is equal to 0 is the vertical line through 0 on the x-axis. And the equation y is equal to x squared is the parabola, just the part in quadrant 1 here. And this is going to intersect right here at positive 1. When x is equal to 1, y is equal to 1. So the region is this little region here. And we want to determine the bounds of integration. We can do either vertical or horizontal rectangles. If we do vertical rectangles, then our double integral, the order of the differentials is going to be dy dx. Now take a look at this integral and determine before actually drawing whether it would be helpful or easier if the order of the differentials was dy dx or if it was dx dy. In this case, the order of the differentials, it would be much more convenient here if the order was dx dy, because you would treat x as a variable and y as a constant, and that would make it easier to evaluate the inside integral. So really it is better to do dx dy here. So rather than do this vertical rectangle, we need to switch it to a horizontal rectangle. Okay, so when you switch it to a horizontal rectangle, that little change here is your dy. The big change here, that big side of the rectangle, is dx. So the differential area of that rectangle, that representative rectangle, is the length times the width. It's always the longest, which is dx, times the shortest, dy. Now you want to determine your bounds of integration. For x, your the left side of the x on that rectangle is x equals 0. The right side of that rectangle, the right side x is equal to whatever x equals on the curve. The curve was y equals x squared, and we want to solve this for x. So if you take the square root of both sides, you get x is equal to the square root of y. That's going to be our right bound for x, or our upper bound for x, which is equal to the square root of y. Now for the lower bound, your low y equals, you slide that rectangle all the way to the bottom, that lowest y is equal to 0, and then you're going to slide that rectangle all the way up to the top to get your upper y is equal to 1. So now these are going to be used in our bounds of integration. We're going to have a double integral of x e to the y squared. Since our rectangle is horizontal, the order of the differentials is going to be dx dy. So our bounds for x are going to be on the inside. So x equals 0, your lower bound, to x equals square root of y. Again, I'm looking right here to determine the inside bounds. And then these are going to be your outside bounds for y. So the y would go from 0 to 1. Now it is important when you're setting up these is that these outside bounds must be constant with respect to those variables inside, and the inside bounds can only have a variable if it's on the outside differential. So you cannot have an x in here if the order of the differentials is dx dy. All right, now we can integrate this. The inside first. We look at the inside integral. It's in terms of the differential x. So we're going to treat x as a variable and y as a constant. So this is the antiderivative of x times a constant, and that's going to be x squared over 2 times that constant. X squared over 2 times that constant, e to the y squared. And then we're going to evaluate that for x equals the lower bound 0 to x equals the upper bound of the square root of y. And then it's going to be all of that dy. So doing the inside, we're going to evaluate the upper bound. You're going to be plugging in square root of y for x. So you get the integral from 0 to 1. When you plug in x equals square root of y, x squared would be y. So you're going to get y over 2 e to the y squared. And then when you plug in 0 for x, you get 0. So now you have a single definite integral. This can be solved using U substitution, or you can approximate it using a graphing calculator, using the integration feature on a graphing calculator. If you're using U substitution, you would let u equal y squared. U would equal y squared. Then your du would have to equal 2y dy. And you have the y and the dy. The only thing you're missing is the 2 here. So if you put a 2 here, you can put a 1/2 out in front. But I would also bring this 2 in the denominator out in front as well. So your integral can be written as this 1/2, the 1/2 here with the 2 down here. You can write this as 1/4 of the integral of e to the u, and then your 2y and your dy make up your du. So that's going to be e to the u du. Now we can adjust our bounds for u. Our lower bound for y was equal to 0. So if you are using this u substitution here, then your lower bound for u when y is equal to 0 is going to be 0. And then your upper bound for u when y is equal to 1 is going to be 1. So it's our bounds are from 0 to 1. Now the antiderivative, this is one of our basic integration rules. The antiderivative of e to the u du is going to be e to the u evaluated at the bounds from 0 to 1. Plug in your upper bound and you get 1/4 of e to the first power minus what you get when you plug in the lower bound, and e to the 0 is 1. So that's going to be your exact answer. If you use a decimal to approximate that, you can check with a graphing calculator using the integration feature of the graphing calculator.